Okay, welcome everybody. I think we'll get started. We're going to be talking about analyzing billion-row data sets with ClickHouse today. My name is Robert Hodges, and this talk was put together with help from our CTO, Alexander Zaitsev. He's not on the call today. I'll be doing the whole thing. If somebody could, before we get started, I'd like to just point out a few features of the Zoom meeting that we're using. You can post chat messages in the group chat. I'll see those, and those. So if you have questions, go ahead and post them there, and I'll answer them either in passing or at the end of the talk. It would be great if somebody could just test that out to prove that we have full connectivity and that you can see my screen and hear me. If you don't mind, somebody please go ahead and post a message to confirm that you have audio and you can see the screen. Wonderful, thank you very much. Okay, let's dive in. So let's get this to go full screen. Just a little bit about us, the folks that put this together. So my name is Robert Hodges. I'm the CEO of Altinity. More importantly for this talk, I'm a complete database geek. I've been working for something like 35 years on databases, plus a number of other topics. ClickHouse is database number 20 for me, although I sort of lose count. It's obviously at this point my favorite one. My colleague who helped put this talk together is the Altinity CTO, Alexander Zaitsev. He's a real genuine expert in data warehouse, including ClickHouse, where he's done numerous large-scale deployments. He's also founder of Altinity. Just a little bit about Altinity, what we do. So we are a provider of software and services for ClickHouse. We'd like to say that we are the best in the world at this. We're incorporated in the UK. Our team is distributed from Berkeley to Moscow, and we have customers worldwide. We are the main US and Europe sponsor of the ClickHouse community. So for example, we just sponsored a meetup in San Francisco last night. We'll show you the list of things that we're involved with at the end of this talk. The business offerings, first and foremost, enterprise support for ClickHouse and ecosystem projects. By ecosystem, I mean things like Python APIs or Golang that connect to ClickHouse and make your applications work. We do that for a large number of customers. We also develop software to make ClickHouse work better. This includes, actually, first and foremost, changing ClickHouse itself. So we have a number of recent additions that we've put in, and we have many more that we're planning. And then we have management software such as ClickHouse Operator, GUI Cluster Manager, and various tools and utilities. And finally, we do POCs and training to help you get your projects off the ground and to get your team up to speed. Okay, enough of the background. Let's dive into ClickHouse. So what I'd like to do is, since I know that not everybody on the call necessarily is a ClickHouse expert, I'd like to just give you a quick overview of what ClickHouse does and how it works. So as you can read on the top here, it's a powerful data warehouse that handles many use cases. It understands SQL. That's very important because most tools that we use and many developers are very familiar with SQL as a language for extracting meaning from data. It's very portable. It runs on everything from bare metal to the cloud. So, for example, in the middle, you have containers. There are a number of very successful deployments on Kubernetes. And we see an increasing number there, but then there are very large deployments just running on racked gear in data centers, and of course, large number of deployments in places like Amazon. Like many data warehouses, ClickHouse stores the data in columns. This is really important because it allows for extremely efficient compression. It also means that if you have a table with many hundreds of rows, you can minimize the I/O because you only have to touch the columns that you're interested in. So this vastly reduces, between compression and the columnar organization, vastly reduces the amount of data that you have to access. And ClickHouse is optimized to do everything as sequential operations, be that a sequential write to lay data down or a sequential read to get it back. Again, trying to optimize the I/O as much as possible. The actual execution of queries is highly parallelized. So ClickHouse is MPP enabled. We'll show you how that works in just a second. It also does what's called vectorized query execution, where we treat because we have this columnar storage, we can treat everything as an array that we iterate down as we're reading, pull the values out, for example, 2-byte ints, and stuff them into the registers of the processor. And because of the fact that we have common data types inside these columns, it means we can take advantage of SIMD instructions. So the scaling is excellent. The data that we're going to talk about today only takes a small fraction of a single host, but there are deployments today that go to hundreds of nodes. The largest one that I know of is about 500 nodes. A couple of final things, open source. So this is a really big selling point for people who are developing applications. And it's not just open source, but it's Apache 2.0, which means that it's not viral. You can package it in your applications, hand it to people without problems. And it's extremely fast. And in fact, a lot of this talk, we're going to be discussing why is ClickHouse fast and how to make it even faster. So that's a lot of data geek language about ClickHouse. I can give you just a simple idea of why we really like ClickHouse and why it's good. Imagine that MySQL, which is a very popular row-based database, runs millions of websites, and Vertica, which is an extremely popular columnar data warehouse. Imagine they got married and they had a kid. This would be ClickHouse. MySQL is simple to set up and operate. It's very portable. Vertica has the SQL capabilities, the column store, wonderful capabilities for compression, time series, things like that. ClickHouse basically has both of them. It's a separate product, but it really combines many of the best ideas from both of them. Let's look a little bit into the ClickHouse organization. I'm going to introduce just enough so that for beginners, if you haven't heard about ClickHouse, you'll get a basic introduction so you know what it's doing under the covers. So ClickHouse, like any SQL data warehouse or SQL database, organizes data into tables. So when we look at the tables, and we'll see examples of definitions shortly, the table is under the covers is going to be partitioned. And what we mean by that is the table is broken up into parts that are indexed and sorted. And this is really important for ensuring that queries are processed quickly. So for example, if we have a table that's reading time series data, we might partition it by month. And what we would do as the data are inserted is we break them up into parts. So a part is a piece of a partition. If you look inside it, it has an index, something called a sparse index, that allows you to find data values very quickly. And it's divided, of course, into columns. And those columns are accessible through the index, which is based on the sort order. Those columns are also sorted. So the values in the columns are sorted in the same sort order for the table as a whole. And then those columns, very importantly, are compressed by default using LZ4 compression, but there are many others that you can use. And so what ClickHouse can do is, because it has many parts, it has columns, it can basically divide up a query, go to all the parts, go to the columns, go to pieces of the columns, and get very high levels of parallelization. Through the compression, through the sorting, it does minimizes the I/O. That's why compression is so important. The sorting allows us to return data in a known order very quickly. So this is the basic organization, and actually, as you see ClickHouse, if you're a user, you'll see direct evidence of this organization, and as you work. More generally, if you have a large problem, you're going to scale out to multiple nodes, and ClickHouse supports this very nicely. There's something called we have local tables, which is what I just showed you, and then you have something called the distributed table, which is a table that knows about the local tables and can basically do an intelligent federated query across them. So for example, in the data that we're going to talk about today, which is New York taxi data, you can have local data, local trip data tables, which contain pieces of the data set. The trip data dist table knows where they're located. There's a configuration file that defines this. And when you do a query, it's going to go to all the pieces. And it does this very efficiently. There's also batteries included replication, so that you can not only shard your data for scaling, but you can also have multiple copies for HA, as well as improving performance if you have a lot of concurrency. These are important features, but we're actually not going to talk about those anymore in this presentation, because a billion rows is actually kind of a small data set for ClickHouse, and we're going to focus on just running it locally on a single host. So with that, I'd like to get started with that exact task, which is data loading. Before you can load data, if you don't have ClickHouse available, you need to install it. Now you can run ClickHouse on Docker. That's the fastest, probably the simplest way to get ClickHouse up on any platform. However, for the type of exercise that we're doing today, I recommend that you either find a Linux host or spin one up in the cloud, whatever, and then you go ahead and install packages. I use Ubuntu typically. Debian, of course, this will also work. And the commands that we show here in red are all that you have to do to install ClickHouse. 19.6.2 is a good and stable version, very recently. So you just install, in this case, the Debian packages, pull them down using apt, run systemctl to start the ClickHouse server, and then you can log in and bang, you're up and running. This takes probably about 1 to 2 minutes if you have a good network connection. The ClickHouse common static package is fairly large. That takes the longest to download. So within a couple minutes, you can be up and running on ClickHouse. The next thing you have to do is, if you have a data set, you're going to have to do a little bit of schema design. We're working with SQL tables here. This is not MongoDB. This is not, we're not working with Hadoop. We can't just throw data into it. We actually have to apply some schema to it. But fortunately for ClickHouse, to get started, the decisions are really very, very simple. So the first thing that you do when you're looking at your data set is you ask yourself, are the fields fixed? In the data set that we're going to be looking at today, the answer is yes, but if they're not, you're going to have to think a little bit about the way that you want to store the variable data. One common pattern in ClickHouse is to use arrays, where within each row, one of the arrays contains the names of the properties, the variable properties you have, and the other another column contains the values. So that requires a little of extra thought. We're going to come back to that kind of modeling in later webinars, but for now we'll assume the answer is no. Now let's say the next question you ask is, do you know your data types? Well, if you're dealing with a fresh data set and you're looking at the first billion rows, it's possible that you don't know the you actually don't know what the value, what are the proper column types, and you can still use ClickHouse very effectively. So in that case, you're just going to define everything as a column with string type. You'll need to have one or two. It's helpful to have 1 or 2 columns when you partition and sort to make those actually have the proper data type. But in general, you can just use strings. And then finally, if the answer is yes, and you do know more about the data set, let's say that it came from MySQL and you actually know what the data types are, then you can define a table with scalar columns with a specific type. So rather than a string, you make it a 1-byte integer or something like that. So that gives you your column definitions. And then the final decision that you need to make is you need to select a partition key. This is what is used to break data up into parts. You like to select a key that's what I call kind of a mama bear solution. It doesn't create too few parts. So like just having 3 parts is not good, but then having 1 million is not good either. So a very common partition key in time series data is divide by month, and then you have a sort order. And this is again something that this just says, hey, how are these data actually sorted in the table, and how will they be? So what order are they going to come back to you? In all cases, it doesn't really matter for your first billion rows if you get these completely wrong, because you can fix it and reload really quickly. So that's basically your schema design. Now, in our data today in the trip data set, we're actually have gone through the steps to figure out what are the optimal data types. So we're using scalar columns, we're using specific data types. We have a time-based partition key, so the partitioning by month, that's the way you do it in ClickHouse. And then we have just picked a sort key that happens to work for our particular use case. So this is typically the end result after you've looked at the data a little bit. You get a nice table like this. So it's very common when you're loading data to get it from CSV. ClickHouse can support a number of formats, but I think for many people, CSV is going to be the most common. So here's an example of commands to read it. So at the top, we show the CSV input data. It's CSV with header values. That's an incredibly handy format because if they correspond to the table names or to the table columns, ClickHouse will map them automatically for you. And to load it, we use the ClickHouse client. If you can load data through the ClickHouse client, I definitely recommend it. It's extremely fast. ClickHouse is written in C++, as are all the utilities, and it has very efficient streaming of data. And in fact, we can if we read the CSV input for headers you see in the first example, it's basically that data.csv file is just getting piped in, and then we tell what database we want to go to, and we give an insert that tells that basically gives the type of insert command we want, and that's all we have to do to load data. Now, for many data sets, it's common to have the CSV compressed, so the second example shows how to read it, for example, when it's coming off gzipped files. So pretty straightforward. So that's the commands to load the data. Now, when you're loading a billion rows, actually it is very useful if you can think about doing things in parallel. This particular data set and the version I'm loading has a few hundred files. The CSV is broken up into a few hundred files. It actually turns out to be about 42 or 43 gigs of data compressed. So if you just ran the files end to end, that would take a while. But we've been working on a project called Altinity Datasets, which will basically allows you to archive and reload data. So it gives you a way of defining the schema of the tables, and then is able to read CSV, including compressed CSV. So project GitHub is shown here, but this is something you can try out to see how to run in parallel. And when we do that, this gives us a kind of nice answer for how quickly can we load a billion row data set. In this case, it's about 1.3 billion rows. So ADCLI is the name of this tool. It's Python. Have some simple parameters that tell us where to get the data set from. And what it does is it goes out, creates the data set, executes your DDL to define tables, and then starts loading the data as quickly as it can. And in this case, to load this relatively large data set took us a little over 11 minutes of clock time. So that's, and we were running, this is on an Amazon MD5 2X large, so not a particularly powerful machine, but it does have NVMe SSD underneath it, so the I/O, the writes are very fast storage. So if we go and look at the data, we can answer the question, well, first of all, we check it's there, so we go in, look at the trip data information, get a count, and we see we have 1.3 billion rows out there. And this actually allows us to calculate how fast did we load that data. So if we run the math, 11 minutes, 4 seconds, we get slightly under 2 million rows a second. And when we initially put this talk together, we were really unhappy with that. What it turns out is that when we run this on this particular VM, because we're decompressing from gzip, we're consuming CPU for that. We're also, of course, compressing as we write to as we're writing to the server, which is on the same host. And so basically we're bottlenecking on CPU. Adding more CPU would get this well over 2 million a second. So it's really quick, and that goes back to the point I made that if you don't quite get things right on a data set of this size, no problem. You can just blow it away and try reloading it. It will come up in about the time it takes you to make a cup of coffee. So that's the data loading. what I'd like to do now is we have the data in ClickHouse. It's in a table. We just did a count on it, so we can access it with SQL. What I'd like to do is begin to look at starting some queries. So one interesting thing that we can do is we can do a little experiment to say what's the maximum performance that we think we could get out of this system. And ClickHouse has a really useful table called system.numbers, where if you select from it, it just allows you to basically generate a sequence of numbers. I assume starting with 0. But what we're doing here is just selecting from it to get 1.3 billion of them and taking the average. And so what this does is it computes the average number. This isn't very meaningful, but what we're doing is testing the speed at which we can scan these generated numbers in memory. So there we get that it runs in 3.4 seconds. That's a useful number. Keep that in mind. Now we're going to go ahead and we're going to do this on the actual trip data set. So we're going to go ahead and we're going to run an average on a number passenger count. This is present in every single record, so we're not cheating. We're not skipping data. And we get an average of 1.6. That's pretty reasonable. That's about how many people you get on average in a taxi. And the question is, how fast is this? So I'll give you just a second to think about it. Is it going to be faster or is it going to be slower than that data that we generated in memory? And that was 3.4 seconds. Well, I won't keep you guessing for long. It's only 1 second. Why is that? Well, it turns out that the data that's generated in memory is a multi-byte integer. And so it's actually generating more data in memory that we have to scan. So in this case, we know that taxis rarely have 255 people, so we just use a single byte int. As a result, scanning that is vastly faster, even though we have to read it from storage. It's way faster than getting the same answer from directly from memory. So this is a really interesting example of how data type as well as cardinality can make a huge difference in performance. What about adding a filter? Let's knock that down a little bit. So we're going to go ahead and do that same average. Here we're going to add a year, 2016. ClickHouse is pretty smart about being able to knock down rows. So in this particular case, by focusing on the year 2016, instead of reading 1.3 billion rows, we read about 131 million. Knock the time down to 162 milliseconds. Then we can add a group by. So we're going to go ahead and group by the location ID, which is basically where the pickup was done. Pickup location ID. It's mapped across, and that's going to be about 1/4 of a second. So that adds a little bit of time. We're doing a little bit of extra work to do that aggregation. So now we can add a join. So we were making this faster by putting a filter on it, but by grouping and now joining, we're beginning to force ourselves to scan more data. And as a result, the time goes up, as you would expect, because there's more work to be done here. We're doing an inner join, and what we're doing is joining with a table that turns that location ID into a nice name for the zone that they were picked up in. And that comes up to about 8/10 of a second. So this is pretty fast. We're working on a very large data set, and for some people, this is already nice. We're not doing any special optimizations, and it's interesting at this point to just think about, just to review some feedback that we've gotten from, or that ClickHouse has gotten from the database community. There's a guy called Mark Litwinchik who does regular performance tests using this New York City taxi data, which is a public data set. And this is, you can read on this slide what he said, is basically this is the first time a CPU-based database has been able to outperform a GPU database. So that's a really, really interesting comment. And we find that overall that on balance, ClickHouse is the fastest database you can find that is, unless you have GPUs attached. I will say that there are projects sort of prototype projects to figure out how to get GPUs integrated with ClickHouse, but there's nothing really to report on that yet. So ClickHouse is fast, but we want to make it even faster, and that's what we're going to do for the next section of this talk. We were at about 0.8 of a second in that join, and what we now like to do is kind of look at some of the things you can do in ClickHouse so that your billion-row data set is going to have even faster queries. So there's a number of things you can look at. You can change server settings, so change the behavior of the server itself. We can fix the schema. We can look at how the columns are stored, and then we can think about how to optimize the queries. So these are 4 pretty obvious things, and we'll give you examples of each of them. Let's look at settings. So by default, ClickHouse is going to try to parallelize queries. And this is one of the reasons, and the fact that it does this efficiently means that it's very efficient. So we're running on a single host. It has 8 vCPUs. These show up as cores as far as ClickHouse is concerned. And what we can do is we can actually control the number of cores that ClickHouse is going to use using a setting called max threads. So by default, ClickHouse is going to just say, hey, whatever number of cores you have, I'm going to use half of them. I'm going to make that the limit. So we can go ahead and adjust that. So we'll try it with 1. So we're going to do that average that we tested before. And if we just have 1 thread, we're going to get almost 5 seconds. If we max it out to 8 threads, it's going to go down to 1 second. So you get pretty good scaling on this. Now there's a little bit of other stuff running on the host, but generally speaking, as you add cores, you get close to linear scaling of query performance. This is something you can play around with. You can have different types of users. For example, users where you just need to have very, very fast response. You can put them in set their queries to use more threads. Users that don't need such fast response and want to run more in the background, you can give them fewer. So very easy to change the query performance. Another thing that's interesting is that the data types themselves matter. And this picture shows a blog post from Percona, where they were doing performance tests on ClickHouse with different data types. So, got a question about KDB. I'll come back to this in just a second. So data types. Let's just talk about what happens when we run a benchmark. And for example, if we're summing numbers or averaging numbers, uint32 versus uint64. So these are numbers that take exactly the different, so they exactly double the size in storage as well as in memory registers. And the interesting thing is that the increase in the increase in response time as you double the number of bytes in the data type is close to 2x. And what this is effectively basically showing is this is the effect of SIMD instructions. So because ClickHouse is optimized to use SIMD instructions wherever possible, when we're summing uint32 numbers, we can actually push twice as many numbers two numbers into the register instead of just 1, and use the SIMD instruction. SIMD means single instruction, multiple data. So basically, you're acting on more than one bit of data at a time in the instruction. So the data types definitely will have an impact. Let's look at some other things that we can do. So schema optimization. So here we have go back to this query with the join, 0.8 of a second. So the question is, can we do this any faster? One thing that we can do is that we can optimize the join. So when ClickHouse is a lot of the performance in columnar databases just has to do with how much data you're scanning in storage and how much data you're manipulating in memory. When we do the join, when you did the join in the original query, the join data was just being added to the row right there. So we're actually forced to process it in memory for every row, but there's an alternative, which is that we're computing aggregates. So we're grouping by. And what we can do is we can push that group by down into into a subquery. So we make most of the work happen on the minimum amount of data in the subquery, and then we do the join at the end on the where we have a much smaller number of rows, and that gets us down to 248 milliseconds. So drop the time by over a third, or over 2/3. So question is, can we do this faster? Well, the answer obviously is yes. So we have ClickHouse. One of the really excellent feature of ClickHouse is materialized views. So the materialized views, if you've used Oracle, if you used other databases, this is a very, very important feature for many databases. And the idea of a materialized view is that an ordinary view is just really a canned SQL query. Materialized view is actually going to pre-compute the query and put some data on storage so that you can do it. There are different types of engines to do this. The one that we're going to look at right now is called the summing merge tree. And basically the summing merge tree, in this case, we're going to go ahead and aggregate the data in advance. So we're going to go ahead and sum the things that we're looking for in that query. And this is, as the slide says, it works as an insert trigger. So as you're posting data into the base table, it's automatically going to be aggregated into the view. As you know we know that these queries run very quickly, so the actual effect on your when you're inserting data is relatively small, unless you have a huge number of views, because ClickHouse is very fast. But it makes a huge difference when we then turn around and run the views. So here's what we're doing. We've defined that materialized view. We're going to actually pull the data in. So it's going to take 303 seconds to pull all the data in. That's about 5 minutes. So the view is now fully populated. Of course, if the view had already been there, this would have been done at the time that we were loading. And then we go ahead and select out of it. So let's do that. And here's the select. So we go ahead and run a select off it, and now we get really, really fast response time. So we're down to 29 milliseconds. And here's another example. So we're doing basic select, and then we're coming back and running that join again. And it looks basically just like the same query we did before. It's just coming back much, much faster. So we're down to 36 one-thousandths of a second. So just to summarize on materialized views, and to come back to something I said, a very, very common use pattern with ClickHouse is to have a basic fact table, which then is connected to one or more summing merge trees, which compute your aggregates. There's a number. We have another example of this at our blog article about time series. These are, in addition to just speeding up queries on any kind of pre-computed aggregates, you can also use materialized views to implement very fast last point queries. A last point query in time series is a query where you're looking for the last reading off a bunch of devices, or for a particular user, or for something that's basically, has a separate time series associated with it. Okay. I think that's it for materialized views. So these are things that we did with the schema. Gives us a lot of nice options for basically answering questions in advance, and also optimizing data types. We've also looked at the ability to change the server behavior by doing sort of altering the number of threads. But that's not all. ClickHouse, if you think about it, there's not one thing that makes it run fast. There are many, and so now what we're going to do is we're going to look at column storage optimizations. So there's three things I'd like to look at: compression, low cardinality, and column encodings. So low cardinality is a really interesting feature. And let's just have a look at how it works. In fact, we can just step back for a second and think about, if you had, for example, that taxi zones query that we think about, we don't actually encode the actual string zone name in each row. In a good data warehouse design, you typically have a bunch of dimension tables that give you the sort of the human readable values of the things that you're counting, or the attributes of the data. But in the rows, you actually store something fairly compact, like an integer. Well, LowCardinality does that automatically for you. So rather than having to create a dimension table or a table of lookup values, what you can do is you can create a table. And this is an example, this test LC table. It's got a string value, and then it's got a LowCardinality value. And so what LowCardinality says is take that string value, but actually create a hidden table that takes the string values and turns them into numbers. And this works really well with data that has low cardinality, which is why we mention this. So for example, something like taxi zones, which have a few hundred values over New York, it's great because it means it's basically going to be a few hundred numbers. So we can insert the data in, and here we're using this insert. I'll just explain. It's kind of an artificial one because our taxi ride data was already optimized. What we're doing is generating some fake data from system.numbers, a long string with a number on the end. And now we can look at something really interesting. We can go to this system.tables table in ClickHouse, and we can compare the amount of compressed data. So for example, that string value is a huge amount of data. If you read it across, it looks like it's 8 gigs. If I'm getting my decimal points in the right place. So actually it may be 84. But the point is, it's a huge amount of data. Now it compresses down enormously. But the low cardinality is very interesting, because rather than storing the string, what's going into each of the rows is just a number. And in fact, that reduces the amount of space that we're using in this column by something like 40, a factor of 40. When you compress, strings compress very well, so strings get high compression rate, but low cardinality, even though these increasing integers don't compress as well by default, you're still getting something that's much smaller. So here it's a factor of over 2 times smaller. So that, since your performance is directly impacted by the amount of data or amount of IOs you have to do, and the number of the amount of data that passes through the CPU registers, this is a huge win. So low cardinality is a we call it a secret weapon. It's a great way of greatly increasing the performance of your database. Here's another example. So we're doing the Humpty Dumpty. Oh yeah. So here's so this is the follow-up example. What it's doing, we showed you the amount of data that we have, and now here's the effect on the queries. So we're going to go ahead and select these values and do counts, and grouping by the string value. If you're just using the string value, it's going to be 11 seconds. You're going to go down to, if you use the value with the high cardinality, it's going to go down to 1.5 seconds. So big difference in performance improvement. And this is because we're reading a smaller amount of data, and we're also materializing less data into memory. So it really improves your performance. Here's another example. Let's look at arrays and think about how those work. So what we're going to do is arrays are a very common data type, as I mentioned, and supported very well by ClickHouse. So we just want to consider what's the performance of arrays when we're using low cardinality. And in fact, we're going to compare an array with low cardinality versus a string. So here we have a string value, and we're going to just basically create a string that has a list of databases in it. You'll see what the data looks like in a minute, and then you can sort of work backwards to what this array is actually doing, or this query is actually doing. And we're going to create an array that's actually the same values, but they're just members of the array. So let's go ahead and look at this. What this is going to generate is some data that looks like the following. So in the S value, the string value, we just have a string which contains the values separated by commas. In the A value, we have the same values, but they're members of the array. And what's interesting, again, is if we look at this at this data, we see uncompressed. There's not a huge difference in the data, but it's still 3 to 1 less because of low cardinality. But this then, it turns out, compresses very, very well because there's actually a relatively small number of values which repeat quite often. So low cardinality helps with scalar strings. It also helps with strings that are in arrays. So this is a great feature and highly recommended. More arrays. Let's. One other thing that's kind of interesting. There is a place where we don't get the full advantage of this, and I'll just highlight this. So it turns out that the like clause processing in ClickHouse is blindingly fast. In fact, the core committers, as I talked last night, and the core committer, or the lead committer, Alexei Milovidov, said that he guarantees this is the fastest. This is the fastest you can find. So, for example, when we select ClickHouse from the string like ClickHouse out of the test array, that runs in 7 seconds. If we go to do a similar thing in ClickHouse using the array, we'll use the has operator. So we'll try and pull ClickHouse out. It's actually a little bit slower. And it's not that arrays are slow; they aren't. But the like clause processing is extremely efficient in ClickHouse, and in fact, the arrays do well because we have a lot less I/O. But it turns out the has operator needs some optimization, and that's something that we're aware of and will be addressed soon. But anyway, in the meantime, it has performance close to like on a string. So in general, ClickHouse is fast, but as we say, it's always possible to make it even faster. This gives you a taste of the types of things that you can do to speed up your queries on your first billion rows. And of course, as your data scales, these become even more important. What I'd like to do is turn a little bit to quickly process some, or just discuss a few integrations that are available for ClickHouse. So you have your first billion rows. You want to be fast, but you may want to also use other products along with it. So there's a great set of ecosystem tools. The libraries are quite good. I use Python a lot personally. Other people on the dev team use Golang. There's a very good driver. JDBC, ODBC, these are all available. Kafka Table Engine to ingest from Kafka queues. Some people use that. A lot of people build their own Kafka clients. It's not that hard to do. Good visualization tools. Data science stack integration, so you can easily move data back and forth between pandas and ClickHouse, and of course you can use the ClickHouse if you're a data scientist. The ClickHouse Python driver works great in Jupyter notebooks, and actually has magic function support for SQL. So there's an ORM that is quite handy. And then finally, there's for those of you running on Kubernetes, I've talked a little bit about that at the beginning of this talk. We've developed the Kubernetes ClickHouse Operator, which allows you to stand up a ClickHouse data warehouse in about a minute, and then scale it up, scale it down, be able to do operations like upgrading it, and a bunch of other really, really nice features. This is something that if you are using Kubernetes, I strongly advise you to look at this. It vastly simplifies the work of maintaining data warehouses in Kubernetes. Other integrations, MySQL is a popular database, and ClickHouse actually has a number of ways that it can access data as well as integrate with applications based on MySQL. So for example, there are a couple of ways that you can pull data from MySQL to ClickHouse. There are external dictionaries, which are lookup tables that then reference MySQL tables, and you can think of it as treating MySQL as a source for an in-memory hash table. And then you can also, through table engines and table functions, you can query and join directly on data. Those are quite powerful. We've actually written a tool for binary log replication. That's one of the Altinity projects. There are other tools out there. Proxy SQL, which knows how to send data or send queries to different locations in MySQL, can also do that for ClickHouse. And one of the the features in the upcoming June release of ClickHouse is ClickHouse will now support the MySQL wire protocol. So this means that if you have the MySQL client, you can just log in directly to ClickHouse as well. Of course, you have to submit ClickHouse SQL since the dialect is somewhat different from MySQL, but the results will come back and be processed using the MySQL protocol. That's a cool feature, particularly as you think about building systems where you use ClickHouse as an accelerator for crunching MySQL data. And of course, there's MySQL, but the other popular open source database is Postgres. So we have a number of similar features, including external dictionaries, table engines, and very interesting one is foreign data wrapper, which basically makes ClickHouse look like a Postgres table, so you get the benefits of the full Postgres SQL dialect, and then the query operations get pushed down into ClickHouse accordingly. So a lot of really great tools here. Let me just touch briefly on the operator, which I talked about. Here's a picture. Just extends what we were saying a few minutes ago. They use a single ClickHouse installation file. And the thing that's really cool about the operators is it basically allows you to create new resources. So just to give you a sense of the value, over on the right, you see all the pieces that you actually have to put together. In all the individual resources you have to assemble to create a real data warehouse. Every distributed application in ClickHouse tends to have, or in Kubernetes tends to have this level of complexity. The ClickHouse operator makes it a single custom resource that you can configure in a uniform and very easy way. So, and then it has tie-ins to doing monitoring, health checks, loads data into Prometheus and Grafana, so on and so forth. It's a really, really great piece of software. I use it a lot when I'm standing up data warehouses and testing things like sharding and replication. A little bit more on where to get more information. You can go ahead and, of course, ask questions, which I hope you will. We're about at the end, so I'll take questions till the end of the hour. And but beyond that, look at the ClickHouse docs. They're very complete. Altinity blog. We regularly post information about how to do. It's more task-oriented. You know, how to solve particular types of problems. There's a blog article that will appear shortly on, for example, on ClickHouse Local, which is a really cool feature. I've done them on networking. Just check out the blog. There's a lot of good stuff there. And then meetups and presentations. This is just a partial list of all the meetups and presentations that we've participated in or helped organize. Actually, Beijing we didn't organize, but every other one we've been very closely involved with. So check them out. For those of you in Silicon Valley, we're planning to have our next local meetup in Silicon Valley on the 13th of August. Still looking for a venue for that, but watch the meetup and you'll see it. And that's it. So I hope this has been useful as an overview. What I'd like to do now is turn to questions. And there's a great one here and I'm going to read the question, which is, you mentioned that ClickHouse is the fastest non-GPU database. Yes. How does this compare with something like KDB for large volumes of time series data? Also, cost aside, are there any major advantage of ClickHouse over KDB? Thanks. Okay, so I want to be completely transparent. We have not benchmarked against KDB, but as far as we can tell, it performs very favorably. What we have benchmarked against is there's something called time series DB, which is or time series benchmark database TSDB or TS. I don't have the acronym in front of me, but it was developed by the Timescale folks, and they published benchmarks in it. We ran those same benchmarks against Timescale and Influx. Just completely unoptimized ClickHouse, which I think you have a feeling for what that means. Just take the schema and just run the queries as they're given. Don't try to do any clever things with low cardinality or materialized views or anything like that. Where we can meet or beat the time series databases, but the time series databases in general, they tend to do somewhat better on short queries, when ClickHouse is unoptimized, we even unoptimized do better on very large queries. Once you put in materialized views, so that, for example, because a place where the time series databases run very well, you get very, the materialized view will allow us to beat the pants off things like influx. So other advantages. Now it's interesting. The reason KDB is interesting, I know this is kind of long, but we're looking at KDB. There's a number of folks in the securities industry that use ClickHouse, and so, for example, a recent addition to ClickHouse is the ASOF join, which is actually a KDB feature, if I'm not mistaken. So there's definitely people looking hard at that, and so we're actually, things that we see that look valuable in those implementations, we're bringing them into ClickHouse. Definitely try it out. I think you'll find it compares very favorably. But if you do find things that ClickHouse is lacking, we'd love to hear about it. Next question. Given that it is a fork, does MariaDB work via the same route as MySQL? Yes, I have not personally tested it, but that's the assumption. Now there are some things that one place where I would expect possible trouble is in the bin log reading. And if I recall correct, it's been a while since I worked in detail in the bin log, but if I recall correctly, MariaDB actually changed the format of the bin log at some point. So tools that can read MySQL may need to be adapted to work with MariaDB. But generally speaking, most of these things are things like the MySQL query protocol. That's pretty standard. So by and large, you should see the same behavior, but I would test and definitely report to the Telegram list or post issues if you see problems. And there's a comment that ASOF is the killer feature. Yeah, we think so too. This is the ASOF, for those of you that don't know what it is. It's a way that allows you to do kind of a fuzzy join between two time series. So for example, the canonical use case that we use is, matching stock prices to weather data. Maybe people like to do that to see if prices are higher on sunny days, something like that. But what you can do is, because those have different time series and the measurements are taken at a different time, what you're trying to do is join a stock price with the nearest, if you will, representation or measurement of weather data. And ASOF is really, really handy for doing that. If you do a lot of time series queries, this is a super useful feature. Let's see. So if you have other questions, I'll stay here for a couple more minutes. These are great questions. Thank you very much. Just let me know if there's other things I can answer. We'd love to, definitely love to hear from you. And failing that, have a great day. Contact information is up here. If you're building apps, definitely come check us out. We do everything from the starter kits, as I said, to the production support, and then of course building features. Any plans on updating materialized views on update delete on the main table? Yeah, that's a really interesting question. So update and delete, as the person asking the question may be aware, are supported, but they're done in a kind of non-SQL-ish way. There is a plan to have them be supported, something more like an update and a proper SQL delete. One of the reasons that this is a difficult operation for ClickHouse is that we have to write. We basically have to go rewrite each part when we delete data, or update it. So it's actually a fairly expensive operation. You can't just go to one row and change something. You have to rewrite the whole part. So that is this question though on getting the materialized views. I do not know of any plans to change what's available out there. Most people use things like collapsing merge trees. So for example, you can have what you can do is basically build build aggregates or materialized views where you basically put a 1 in one of the columns, and that means, hey, the row is inserted. You put a 0 when it was deleted. So the aggregates, when they're computed on that type of materialized views, will automatically show values for the last inserted row, or if the last operation on the row was deleted, they won't show it at all. So as far as I know, that has not changed, but that's definitely a great question. And in general, I will say in general, I've dealt with this issue quite a bit in Hadoop and other places. What you usually do with bin log data, for example, or data coming from OLTP databases, is you copy the whole bin log in, and then you go through essentially a view process where you sort it and throw out everything that's been deleted and just keep the latest values. I think in terms of storing facts, it's better to do it that way because it also allows you to reconstruct the history. So that may not be the case for all use cases, but for many, that's definitely what people want to do. Good. Okay. I'll wait 60 more seconds, see if there are any final questions, but so for everybody else, thank you very much. There will be a recording of this, and we'll post the slides. Delighted to have you on today, and thanks for checking out ClickHouse.